The function of cylinders with a piston rod is very simple. A tube, closed on both ends with a cap and heat, has a drive piston. The double-acting cylinder, as shown here, has two inlet ports. The movement of any cylinder is triggered by compressed air. High pressure on one side drives the piston to the other side. Here the piston force can be built up in both sides. That's why this type of cylinder is called a double-acting cylinder. This piston force can be calculated by the law of Pascal. If you have pressure on both sides, the effective piston force is the difference of the forces on the piston and rod side. Normally, double-acting cylinders are actuated by a directional spool valve with 5 ports. Our way valve shown here has 2 switching positions, so you call it 5x2 valve. The way valve directs the compressed air on port 1 to the air ports of the cylinder. Exhaust air from the cylinder is directed to exhaust ports 3 and 5 with these pneumatic mufflers attached. When the piston hits the head or end cap, it creates a hard shock. Besides the stress on the cylinder components, it is noisy and transmits vibration to the machine. Cushioning is a possibility to decelerate the piston at the vicinity of the caps to prevent these hard shocks. By trapping a certain volume of air in the end position, a braking effect can be generated. With an adjustment screw, you can get the ideal cushioning. Too much cushioning results in slow strokes, and too little cushioning increases the end-of-stroke shock. Especially for sequence controls, you need to detect the end positions of the cylinder. Here, reed sensors are mainly used. To be able to use these sensors, the piston is equipped with a magnet. So when the piston approaches the reed, you get a signal to the control. In summary, double-acting cylinders can have long strokes, up to several meters, with a constant output force through a full stroke. They give the user full control as they can be stopped in any position. But in case of a power loss or pressure failure, you don't have a defined cylinder position. In addition, the air consumption is relatively high as you need compressed air to retract these cylinders. In single-acting cylinders, only one chamber is inflated with compressed air. That's why a piston force is built up in only one direction. The inbuilt spring has the only function to retract the piston automatically when no pressured air is switched to the cylinder. Depending on how this spring acts within the piston, you can distinguish between 2 different types of single-acting cylinders with different base positions. Base position minus is the common one. As the single-acting cylinder has only one inlet port for the compressed air, you would use a 3x2 directional spool valve. In our example here, we use a spring-loaded directional valve. Due to the inbuilt spring, the piston returns to its base position in case of a power loss. Besides this, the air consumption is about the half of a double-acting cylinder of the same size. However, this inbuilt spring leads also to an inconsistent output force through full stroke and less efficiency due to the opposing spring force. In addition, the stroke is limited by the spring length ability. In general, single-acting cylinders offer a relatively short stroke compared to the double-acting cylinders. Whereas a traditional pneumatic cylinder uses a rod to push or pull the load from the piston, a rodless cylinder moves the load alongside its piston. As a result, you get the same stroke length but in less space, same force in both directions, and no rod buckling with high loads and long strokes. Different types of rodless cylinders can be distinguished by the way the piston is connected to the carrier. One principle is the magnetic coupling. Here, the piston and slide are connected together by using permanent magnets. One magnet integrated within the slide, the other one within the piston. In this design, the piston can move in a completely enclosed thin steel pipe. You get a leak-free cylinder with less wear compared to the other types of rodless cylinders and no ingress of contaminants. However, the magnetic coupling is also a force limiter. If the load is too high, you have to worry about decoupling. If you want a rodless cylinder with a high cylinder force, you would choose a slotted rodless cylinder. Here, the piston is mechanically coupled to the carrier. An inner and outer band keeps the air within the barrel of the cylinder. But how so? As the piston drives, the two-band sealing strips open in front and then close behind, regardless of the direction of travel. The seals of the piston inside the cylinder barrel press the inner band tightly against the barrel of the cylinder, preventing air leakage. The outer band is pressed tightly against the outside of the slot of the cylinder barrel with the so-called shoes of the carriage. And it's working! Here you see a band cylinder totally dismounted and fit together again. Inner and outer bands may wear over time as they stretch. As a result, you can get air leaks and loss of air pressure. It is up to the maintenance to replace these bands, especially for expensive cylinders. The last type of rodless cylinder is the so-called cable cylinder. Here, a cable is connected to the piston and drives the carriage through a pulley on each end. This is a very simple design. That's why cable cylinders are relatively inexpensive. But the weak point is the cable itself. Cable wear causes inconsistent positioning, and leaks can occur from stretched cables. You need extra distance? Then take a telescoping cylinder. Also called a multi-stage cylinder, this type of cylinder consists of a series of tubular rods called sleeves. These sleeves sequentially decrease in diameter and are nested inside of each other. Once pressure is switched to the cylinder, the main sleeve first extends. Once this sleeve is fully extended, the next smaller one begins to extend. Telescoping cylinders provide an exceptional long output stroke from a very compact retracted length. They can be designed as single-acting or double-acting cylinders. Pneumatic rotary cylinder converts compressed air pressure into a rotary motion. One of the most widely used designs is the rack and pinion rotary actuator. A long piston with gear rack teeth meshes with a pinion mounted to an output shaft. The output shaft of this double-acting cylinder rotates counterclockwise by pressurizing the right-hand chamber. Compressed air on the left-hand chamber produces clockwise rotation. Rack and pinion rotary cylinders offer a wide range of torque and rotation. They are mechanically stable and provide radial load support. Vane cylinders have a cylindrical chamber in which a vane is mounted to a central shaft. Air pressure on one side forces the vane to rotate until the end of the stroke is reached. You get vane actuators in two designs. The single vane design has a relatively large rotary motion, up to 280 degrees typically. The double vane type offers a less rotational range, which is limited by half but produces twice the torque. This type of rotary cylinder uses external methods to limit the rotation or to cushion the load. The end position of our cylinder here is detected mechanically. Compared to the rack and pinion cylinder, vane actuators are compact in size and less expensive, but the cycle life is limited by the wear of the vane seals. Also, friction caused by the vane seals and leakage over these vanes result in less efficiency.